Hi, today we're going to be talking about integration. In this chapter, we're going to consider integration calculus. So this involves anti-differentiation, which is the reverse process of differentiation, and we're going to be looking at applications such as finding the area of a curve. So let's look at finding the area of a curve. So let's consider the function f of x equals x squared plus 1. And we wish to estimate the area A enclosed by U of f of x, the x-axis, and the vertical lines x1 and x4, as seen here, x1 and x4. Suppose we divide the intervals between 1 where x is more than 1 and where x is less than 1, where x is more than 1 and less than 4. Into the 3 strips with width of 1 unit, and we obtain the 3 subintervals of equal widths. So those are just 1, 2, and 3. The diagram along shows the upper rectangles, which are the rectangles with the top edges at the maximum of the curve on that subinterval. So we can see that those are the 3 subintervals. And then to the right of that, we can see the lower integral rectangles, which are the rectangles with top edges at the minimum of the curve on that subinterval. So we can calculate the area of this, and then we can calculate the area of that to see the maximum and the minimum area that the area under the curve could be. So the area for the top one will be just simple 1 multiplied by f of 2 plus 1 multiplied by f of 3 and 1 multiplied by f of 4. We can just do some simple math there and we get 32. Now let's do the same thing for the lower one, and we get 17 units. Now this gets a bit more, well, you have to pay attention close to the math. So we can see that the area of the lower is less than the actual area, but the area of the upper rectangles is more than the actual area. So the area lies somewhere in between 17 and 32 units. If the intervals between 1 and 4 were divided into 6 subintervals, each width of a half, then we would get something between 27 units and 20 units, which is a lower range. So that means if we made the intervals, split them again, where we had 12 units, the upper and lower areas would come even closer. So now let's imagine that AL and AU will become more accurate as the width of each of the columns is smaller. In fact, let's say that they converge to 1A with a very, very small width, almost, well, basically it doesn't exist. And that's how you find the area. That's what integration is, and that's how you find the area of under the curve. So the value A is known as the definite integral of f of x from A to B, written as A equals the integral. This is a sign for integral. From A to B of f of x dx. If f is bigger than 0 for all values in between a and b, then the integral of a and b of f of x dx is equal to the shaded area of the diagram. This is just a general formula. So anti-differentiation and the fundamental theorem of calculus is what we're going to be talking about in the next few slides. So as the name would suggest, the process of finding y from dy dx, or f of x from f prime, is the reverse process of differentiation, which we call anti-differentiation. This is a simple diagram to just remember what it is. So what is the fundamental theorem of calculus? From the geometric argument above, we can see that this is a geometric argument that we were talking about at the beginning. The fundamental theorem of calculus can be stated in 2 forms. One of them is if x is equal to a of t is equal to a to t f of x dx, or more commonly we can just say in between a or b. And then to find the actual area, we just substitute the a and substitute b into capital F of x, which is the antiderivative of f of x, to get the actual area. We're going to be talking how to find the capital F of x later. So some properties that integrals have are the following. I won't read all of them. We can read and then make sense of them. But they're pretty intuitive. For example, if the range is between a and a, the integral is 0 because the area is between one value, thus there is no area. Similarly, if there is an integral between a and b of c of a constant, then the integral is just c and the difference between b minus a, which is common sense if you just draw out the diagram and then try to calculate the area yourself. Let's try an example of finding the area under a curve. So let's use the fundamental theorem of calculus, which connects the area under the curve and differentiation and anti-differentiation to find the area under the curve. So if f of x is x squared, let's do the reverse of differentiation. So instead of decreasing the power by 1, let's increase the power of 1, so we get x cubed. And then instead of multiplying by the power, let's divide by the new power, so then we get x cubed over 3. Now, once we have the capital F of x, we can just substitute a and b, or in this case 0 and 1, to get the following formula, and then we know the area under the curve is 1/3 of unit squared. Pretty simple. Let's see some rules of integration. For example, if there is a constant, it can be written in front of the integral sign. Similarly, the integral of a sum is the sum of the separate integrals, and this rule enables us to integrate terms by terms. So for example, if you have two areas that are next to each other, you can integrate them by adding them together rather than integrating them all at once. Some more rules of integration are these. I won't read them out, but you can look at them for yourself. For this math course, you don't need to know proofs for all of them, but you might need to know proofs for some of them, such as the one that's shown earlier. And here's another diagram just to help you if you want to take a picture of this or something to help you memorize them.